from what we've seen in our sampling distributions, when we looked at sample means, we saw that their distribution followed a normal curve centered at the mean of the population and had a corresponding standard error. And also, when we did proportions, we also saw that the p-hats had a sampling distribution that was normal. And it's also centered around p. So the variances, what's interesting about them is that they also target the variance of the population, but their distribution is skewed right, always skewed right. So all the sample variances of the sampling distribution would form a skewed right distribution. But they will target the population variance. So what we've found so far is that the unbiased estimators, the statistics that target the value of the population parameter are the means, x bars, the variances, s squared, the proportion p hat, and the ones that do not, that are that are biased estimators, are the median, the range. There's more than this, but some of them, standard deviation. Now the trick with standard deviation, though, is that the bias is small, and you can also use the relationship that standard deviation has with the variance to do a hypothesis test for standard deviation. So we kind of do a workaround to test for standard deviation. So we are going to test a claim about the population standard deviation or the population variance. So we're going to use our formal method of hypothesis testing. These are all your variables. You've seen them before. N is sample size. S is sample standard deviation. S squared is sample variance. And then the population standard deviation is sigma, and sigma squared is the population variance that's claimed. And we've got requirements, just like we had in previous sampling distributions. The sample has to be a simple random sample. The population has a normal distribution, so again, it's a very strict requirement for testing with variance and standard deviation. The test statistic looks quite different from our other test statistics, but it will be used in the same way. So notice, because the chi-squared distribution is always positive, our test statistic will also be always positive, and it has to do with squareds. We take the factor of the sample variance over the population variance, and then we also need degrees of freedom. N minus 1 is our degrees of freedom, and N will again be our sample size. Okay, so here are some properties of the chi-squared distribution that are a little different. Before, we always dealt with a normal distribution that was symmetric. Notice the chi-squared distribution is skewed right, so it is not symmetric. The other property that's similar to the t distribution is that it's based on degrees of freedom. So here's an example of a chi-squared distribution where the degrees of freedom are 10. And then when the degrees of freedom are 20, it kind of moves a little differently. But it's still going to be skewed right, and it's definitely not symmetric. We're still going to do, when it comes to the variance, we're going to have right-tailed tests. So a right-tailed test would be, there's my test statistic, and then my p-value would be on the right side here. And then a left-tailed test, I want a different color, but a left-tailed test would be my test statistics over here on the left, and on the area to the left is my p-value. And then there's still also a two-tailed test. Okay. Before, we used normal CDF or TCDF to find those p-values, and just now we're going to use the chi-squared CDF function on our calculator. So very similar to what we did before. We'll use that for the p-value. So in this example, we have a common goal in business and industry is to improve the quality of goods or services by detecting variation. And quality control engineers want to ensure that a product has a consistent quality to it. So this is why variation and standard deviation come into play. Now, weights of coins have a specified mean, but if it has too much variation, some will have weights that are too low or too high. And vending machines basically work on the base of the weight of the coin. So we're going to have a simple random sample of 37 weights. So in this example, our n will be 37. And in this sample of 37, we obtained a mean, so it's a sample, so that's x bar, of 2.499, and we got a standard deviation of 0.01648. Sorry. And they want us to test the claim, that the population, oh gosh, I'm so sorry. The population weights has a standard deviation less than the specification of 0.023 grams. So that we find, I don't know why it's not letting me do this, but oh well, it keeps moving. But that's our test. So we are testing the following claims. We're testing that the standard deviation is less than what the mint specifies, and our null is that it is what they want it to be. And this is all the data that we obtained from the sample. So we've got our null and our alternate hypothesis, and our alternate is the one that we're testing. And just like we did in past hypothesis tests, we check our requirements. Our requirements are that the population has to be a simple random sample. We were given that. And then the original population has to be normal. So if we have these two things in play, what that tells us is that the variances will follow a chi-squared distribution. And we're not going to even worry about the rest of it, but it'll follow a chi-squared distribution with degrees of freedom equal to, in this case, 36, because that's n minus 1. So our chi-squared distribution, what's interesting about that, again, it's skewed right. And notice that because it's squared values, the smallest square is 0. So it doesn't go on to negative infinity. It stops at 0 on the left. And our test statistic, chi-squared test statistic, is now going to be this formula, n minus 1 times s squared over sigma squared. And when you plug in the values given in the problem, you should get 18.48. And notice 18.48, sometimes it's hard to know where they are in chi-squareds, but I'll put it right there. And I know that this is a left-tailed test, so my p-value is going to be the area to the left. It's kind of messy, but my p-value will be chi-squared CDF, and I'm going to go from 0 to 18.48, and I've also got to remember, sorry for the going off the page, my degrees of freedom will be 36. When I do that, I obtain a p-value of anybody remember what my p-value was? People? Oh, 0.0069. So that's my p-value, which is very low, so I'll reject the null hypothesis. I'm going to leave the rest for you to finish with the conclusion, because I got to go. Have a good night.